Okay, let's start. So we'll continue the discussion of stable models. And last time we looked at the stable models of positive program and definite program, where basically stable models are just minimal models of the program. Okay, so the question is, why do we bother with different terminologies? So from today, they will be different. Okay, when we go to a program that is more general than a positive program. Okay. All right, so let's recall what is Clingo program. So first, it's a slightly different terminology, but basically the same idea as in first order logic. What do we define as an atom? Atom is something this minimal, smallest unit that we can assign the meaning of true and false. So in the terminology of Clingo, an atom is a symbolic constant followed by a list of terms. Okay. We also allow another kind of atomic formula, which is a comparison. Although this is actually allowed in first order logic, where in Clingo we make it more explicit. So what is a comparison? Comparison is a relation between the two terms. Okay? So it can be equality or inequality or less than or greater than. Okay? So these are the comparisons. And the comparison usually makes sense when you have numbers. So some number is greater than the other. But also you can actually technically compare the other symbols. Okay? So some John is greater than Mary. So this kind of relation is also possible. It's because it's basically looking at the code, okay, and the Unicode and see which one is actually greater. Okay. So what are the Clingo rules? Clingo rules have this form. Basically, what you have seen before as a program. So it is a conjunction of atoms or comparisons, like H1 through HM, okay? So that's one kind of Clingo rule. Now note here that there is no other connectives than the conjunction, okay? So the second rule here is saying that this is also the comma separate list of head and comma separate list of the atoms and comparisons in the body. And note here that unlike the rules that we defined maybe last week, it's a bit more restricted because you have only atoms and commas. Okay, so you don't have the conjunction and disjunction and negation nested arbitrarily. Okay. Now another confusion that might come here is the meaning of comma in the head and body are actually different. So we'll get into that soon, but roughly speaking, the comma in the head, that is between this HI and HJ, they denote disjunction. Okay? And comma in the body represent conjunction. Okay? So throughout the today, we will use this convention. So something in the head, comma separated atoms and comparisons are actually disjunction over those atoms and comparison, and the body is actually conjunction of those atoms and comparisons. Okay? It might be a bit confusing sometimes, but there is some reason that the designers of Clingo language chose this way. They don't have to worry about much overloaded symbols. So as long as you remember where the comma occurs, the meaning is actually not ambiguous. It could be confusing if you are not used to this convention, but once you got used to it, that's actually no problem. Okay? So here is an example that you see. So worm of C, if T of C comma T1, T of Austin comma T2, T1 is greater than T2. So we are going to get into this meaning soon, but basically this is just a syntax. Okay, so this is a second type of the rules where you have the implication symbol represented as colon dash, and you have a conjunction in the body. Now, most of the time, you will see that the head is very simple. It's just on one atom. Okay? I'm not sure how to do this. Okay, good. All right. Another convention is there are variables and constants. So in first order logic, we declare what are the variables and what are the constants. Constants belong to signature. Now, in the language of Clingo, you don't have to define the signature explicitly, okay? And that actually gives a lot of convenience. But one convention here is when you write a capital letter, that's actually the variables. Okay, so when you see the C, T1, and T2, these are some variables that range over other constants. Okay, now you will see that what is then the universe that the variables range over. Okay, so that I'm going to talk maybe in a few slides later. So, so here we talk about Clingo rules in general that have variables. Now the variables are understood as just placeholder for the constants. Okay, so here is a terminology. So when you say instance of a rule, is a rule that is obtained from these rules that have variables, where the variables are replaced by some particular instances, okay, particular objects in the universe. And we are going to do exercise on that today. Now, where these values come from, in first order logic, you have to specify the universe in separate, right? So depending on which universes that you are given, then the whole interpretation also changes. On the other hand, there's actually only one universe, right? Actually, no. Let me say it this way. There is actually not much of that generality in the language of Clingo. Okay? I cannot say actually the universe is only one, but it could be actually multiple still. But the values that you are substituting for, replacing with, they come from two sets. One is S, another is Z. Okay, so Z is a set of all integers. Okay, now what is S? S is some constant that is not integers. Okay, now what you might ask, what is that then, this set of symbolic constants? Do I have to specify? As long as this set S contains all the constants that occur in the program, you don't need to. Okay, so when you get to the example, we'll see soon. But what we are going to do now is when we have the rules with variables, then this rule actually represent infinitely many possible instances, because obviously a set of integers is already infinite. Okay, all right. So let's look at this. So I said the instance of this. Okay, so what is the instance of this? And we'll get into more concrete example, but for now you can see that these C, T1, and T2 will be replaced by some members of this S union Z. So here I have V0, V1, V2. They are members of the set S union Z. Okay, so once you have the set S and Z, then you know what the variables range over. Okay, are we together? Okay. And here, we are going to understand the Clingo program as first turn into propositional image, which means that you replace all the variables with constants in S union Z. And then we understand this rule, which we call ground rules, that means there is no variables in the rule, we rewrite this as a propositional formula. Okay? So this is actually very straightforward. The symbol colon dash, you just understand as an implication. Okay? And this is the thing that you need to know. So we already covered the first one. As I said, the comma in the body, so if you see the comma in the Clingo rule, turn this into conjunction when you turn into propositional formula. Similarly, for comma in the head, you turn into disjunction. Now you will see the symbol NOT in the language of Clingo. It's just a negation. And there are also these special symbols, false and true. In propositional logic or in propositional formula, you write as a bottom and top. And then it goes back to the propositional formula that you saw before. Okay? So Clingo program is just one convention to write some particular class of propositional formulas. Okay? So, yeah. So each of the expression in the, well, actually, I think I switched the order. So I said look at the propositional image and then turn into the formula. Actually, doesn't matter. You can actually do the opposite order too. You can rewrite this as a formula way and then turn into the image. Okay. That will result in the same. Okay. So let's look at this example. So a simple database. This is the temperature of each city. Okay. And what the knowledge that we want to express is this. So we want to say that city C is a warm city if the temperature in C is T1 and the temperature in Austin is T2 and T1 is greater than T2. Okay. The reason that the cities in Texas was selected here was because the author of this note is from Texas. Okay. All right. So, believe it or not, according to this definition, as long as the city's temperature is warmer than Austin, then this city is considered as a warm city. Okay. So let's see. Is Austin a warm city? According to this definition. No, I mean, the temperature has to be greater than the temperature in Austin, so it's not. How about Dallas? Yes. Houston? San Antonio? No. Okay, so we want to derive this simple reasoning. Okay, so this is just very simple inference. So here is maybe the first Clingo program, the complete Clingo program that you see. So to write the database in Clingo is actually easy. Okay, it's just table entry. You turn it into atom. Okay, so T represents temperature. So temperature of Austin is 88. Temperature of Dallas is 95, and so on and so forth. Okay. Now each of these things, I wrote this as a one line, but in fact each of these has one rule, and each rule is separated by the period. Okay, so there are actually 1, 2, 3, 4 rules, and the next 5. So there are actually 5 rules in this program. Okay. So yeah, nothing special, right? So note here that we are writing a declarative sentence. So we want to find a city that is warmer than Austin. We are not giving algorithm to find it. Okay, you can, but there's no need to do that when you use this language. So you just explain to the system what you considered as a warm city. And you ask Clingo, and you find all warm city. Of course, this is very simple example. So you might think, well, why do we bother? Soon it will be more clearer when you have more complicated example. But I'm going to use as a running example for today, maybe also the next class, just to show you some point. Okay, so now let's think about what is the propositional image of this program. So when you have the first 4 rules, they are already grounded, which means that no variables to replace. So that's okay. So they are already propositional image. Okay. Now what about the next rule? Now the next rule is a bit tricky. Now you have to replace C and T1 and T2 and so on. Okay. So this is actually the propositional image. Okay. So here I write V1 and V2 as just some meta variables that range over all possible values in the set S union V. So V1 and V2 I wrote here can range over any constants and any integers. Okay? So I can actually see that there are actually two cases. Okay, there are two cases where V1 is greater than V2. Now what V1 and V2 can be, that's any element from S union Z. So it could be maybe Austin greater than 88. That's actually also possible. Okay, but most of the time what makes sense is when this is a number. Okay, so V1 is a temperature of one city and V2 is a temperature of another city. However, by definition so far, V1 and V2 can range over any elements. Okay? Now, what I wrote as a top and bottom is obviously coming from the this symbol, right? So T1 is greater than T2. If this relation is satisfied when you replace T1 with some element V1 and T2 with some element V2, okay? And this particular instance V1 and V2 satisfy this relation, then we replace the comparison with top, okay? For some reason I cannot write now. Let's say, so V1 is, let's say 2, V2 equal 3, or let's say I should write 4, okay? So in that case, the instance here will say, okay, let's say V0 equals maybe Phoenix. This particular instance satisfies that condition, right? Now note here that Phoenix is not even in the even mentioned in the program, but it is actually okay. Okay, so any values. In fact, you will see that V0 can be 4, V1 can be 5. Actually, could be. I think it could be Austin, and V2 could be. I think Austin is greater than 3 according to the Clingo language. So this is actually also fine. Okay, as long as these V0, V1, and V2 come from this set S union Z, where S is a set of all symbolic constants and Z is a set of all integers, that is fine. Okay, so there are actually infinitely many possibilities here. Okay, so here you will see actually infinitely many rules, but not all of these rules are actually interesting. Now, one thing that you will notice is this rule that has bottom, where V1 is not greater than V2. Okay, then this substitution will result in bottom, right? This rule is actually harmless, right? Because the rule is always true, right? So if you have the body that has bottom, the body cannot be satisfied. So it is actually okay to disregard this rule. Okay? So if you have this, what remains is actually these two rules that you see. In fact, you can actually further simplify this. Okay, so this requires a bit of thinking, but let's see. So idea is if the body is never true, then this rule cannot be, doesn't matter, right? You can delete this rule. Now note here that among the instantiation of this rule, okay, suppose I wrote maybe Phoenix in place of V0. the rule is actually always true. Do you see why? So regardless of V1 and V2, let's say this is Phoenix. I can actually write maybe, what is current temperature?
There is no
I don't know. Let's say 100. Okay. Now Austin is actually 88. Let's actually use this value. Okay. So if you have this instance, one of the instances will have like V0 is Phoenix, and V1 is 100, and V2 is 88. That's actually possible values, right? But this rule is actually not useful because Phoenix or 100 cannot be proven from the database. This is always false. So you don't actually need this rule. So what matters is the possible instances that may make the body to be true. Only that case we actually consider. Okay, so those are the rules that actually matters. If the body cannot be true at all, then we don't bother. Okay, so let's actually go back. So then, what is actually the thing that matters here? So V1 should be greater than V2, and the temperature should be mentioned in the database. And then you will see there are only two ground rules that matter here, where V0 is Dallas, and V1 is 95. Okay, and V2 must be 88. Okay, that's one instance. Another instance is V0 is Houston, V1 is 90, and V2 is 88. Other substitution will make the body simply false. So you don't have to worry about it. Okay? Now what this tells us is actually an interesting thing. You don't have to worry about the universe. Okay, I didn't actually give the universe explicitly. I said there's a set of all possible possible symbolic constants, and all the set of integers. You might think that, well, there's too many. Okay, maybe that's undecidable if you have infinitely many rules to consider. It turns out that that's not the case. Okay. Also, you will also note that in first order logic, you can map constants to any values in the universe. Okay. Here, integers are mapped to integers, and constants are mapped to itself. Okay. You don't need to worry about whether the constants 1 is mapped to 2. That is possible in first order logic, but not in here. Okay. Questions so far? Yes.
So if the Clingo allows integers, why doesn't it allow real numbers?
Yeah, that's a good question. Clingo actually allows real numbers in certain ways, which we probably don't cover in this class. But historically, the real numbers are not allowed because when you substitute the values, the number of rules can be infinite. In fact, Clingo relies on the fact that the ground rules are finite. Okay?
But for integers also there are infinite integers.
Integers are always infinite. However, Clingo accepts a program where this instantiation with respect to the infinite set of integers always generate finite number of ground rules. Okay? So we'll see more clearly about that. But for now, let's just say that even though you allow the universe to be infinite, okay, in many cases you will generate finite number of rules. This is not always true. Okay, so one of the things that you will encounter when you run the Clingo program, the Clingo sometimes complains, even for the valid syntax. One of the things that happens quite often is Clingo complains that the rule is unsafe. Okay, so unsafe basically means that the number of rules that are generated by this substitution is infinite. Okay, so we'll actually get that probably today. So, all right. So the whole story here is this thing can be understood as this thing. Okay. So in terms of the symbolic constants, you don't actually need to worry about the constants that do not even occur in the program because they will never make the body to be true. In terms of integers, you may have to worry about those integers that are not even appearing in the program because there are some arithmetic that you can do. Okay? All right, so okay, so when I said propositional image, I actually simplified some part there. One thing that is a bit complicated is when you have this interval notation. Okay, so you remember when we evaluate the terms, the interval was, let's say if you have 4 dot dot 5, that means 4 and 5 as a set of values, right? Okay, so that notation is actually there, but the problem, the difficulty here is when it occurs in the head and body also makes certain difference. Okay, so we'll see the example. Let's just read for now. So if you see this interval, term of intervals in the atom, okay? So if it occurs in the head, it means a conjunction. If the same atom occurs in the body, it means disjunction. We'll see the example soon, but let's just remember that sometimes when it is head, it's a conjunction. When it's a body, it's a disjunction. Similarly, if you have a comparison, so previously I saw there was only one value that each of T1 and T2 result in, so it's not quite complex to do. As long as this comparison is satisfied, is true, then we replace with top, otherwise we replace bottom. However, these T1 and T2 can be also set of values each. Okay? So T1 can be 2, 3, 4. T2 can be 3, 4, 5. Okay? Now, when you have this kind of case, also it matters whether this comparison operator occurs in the head or in the body. Okay? If it occurs in the head, it works like a conjunction. This T1 less than T2 must be true for all possible values of T1 and T2 when it occurs in the head. If it occurs in the body, it works like a disjunction. If at least some of the values of T1 and some of the values of T2 makes this comparison to be true, then this is true. I know it's confusing, okay? So I prepared some examples, okay? Just remember some difference between this, and we'll come back to this, okay? So let's just do the exercise here. So here, HI means that this is one of the head atoms, okay? Okay, the atoms that occurs in the head. Now, this is P1 dot dot 2, okay? So there are two, so where does it correspond? So let's call it 1, 2, 3, 4, okay? Which case does it correspond? It's 1, because it occurs in the head and it has the dot dot notation inside, so it's exactly that, like this. T1 is 1 and T2 is 2. Okay? Now in this case, it should be the conjunction of all formulas. So what should be the formula here then? P of 1 and P of 2. Yes, that's correct. P of 1 and P of 2. Good. Then what about this one? Now it occurs in the body. It's a disjunction. It is now the second case. Okay. What about this? Now note here that we can use arithmetic expression here. So P of 1 divided by 0. Now Clingo understand this as an integer arithmetic, of course, but 1 divided by 0 does not make any sense. It's undefined, right? So there's no values for 1 divided by 0. Okay? So then what will be the case? If there's no value, but do you have to make a conjunction or disjunction? Conjunction, because this is the first case, right? Empty conjunction is equivalent to what? True. It's a top. Okay? So we turn into this. Okay, if you don't know why empty conjunction is top, for now let's just memorize it. Okay, I can explain later. Or if you take logic course, there's a reason why we do this way. Okay, but for now you can just understand empty conjunction is top, empty disjunction is bottom. Okay. What about this? This is also empty thing, but is either conjunction or disjunction? It is actually the disjunction because it belongs to the second case. Empty disjunction is actually bottom. Okay, good. Now, interval. So, equality between two intervals. Now, this comparison occurs in the head. So, which case are we in? 1, 2, 3, 4. Is a 3, right? So, this comparison occurs in the head. And when in this case, every value of V1 and every value of V2, this relation has to be true. Now, what is the value of 1 dot dot 2? So 1 dot dot 2, what is the value? It's a set consisting of two values, 1 and 2. What about the values of 2 dot dot 3? Of course, 2 and 3, right? According to the third case, every value that you pick from the first set should be equal to the every value that you pick in the second set. Is it true or false? It's a false. So what do we do? The bottom. What about this case? Now it's not every, but it's some T1 and some values of T1 and some values of T2 are equal, then this is true. And this is actually the case. Of course, if you choose 2 and 2 from each side, then 2 equals 2. So this is top. Okay? So I know it's a bit confusing, but once you got used to, you may write many programs in a very succinct way. Okay? Any question up to this part? Yes.
So in the head, we always saw disjunction of atoms in the Clingo rules.
Not necessarily. Not necessarily. So, well, so for example here, okay? So when you have this 1 dot dot 2, this is actually the conjunction. Okay? When you use comma, that's a disjunction. Okay? So when you say P1, comma P2, this is actually P1 or P2. Okay? There's a few slides back, we had this meaning of comma is actually different when it occurs in the head or in the body. Okay? So, yeah, so you can actually express both conjunction and disjunction in the language of Clingo. Okay, so it's slightly different way. Yeah, okay. Yes.
So can you explain the last one?
Last one is what? The comma? Or the B, J equals 1?
BJ, 1.
Okay, so yeah, good. So the values are actually the same as before. So 1, 2 means the values are 1 and 2, and this means 2 and 3. Now, according to the definition, this thing is now in the body. Okay, so B is something occurs in the body. So this becomes true if for some values V1 and for some values of V2, this comparison holds. So I can choose one value of 2 from the first, the left-hand side, and 2 on the right-hand side, okay, because sum means I can choose, right, and they are equal. So this is top.
This is like intersection should be at least one element.
Yeah, that's what it means in the for sum. Okay, so it's basically if you see anything in the body, it works like a disjunction. Okay, so when I say 1, 2 equals 2, 3, that means either 1 equals 2, or 2 equals 2, or 1 equals 3, or 2 equals 3. If this disjunction is true, then this is true. Did you get what I was talking about? Maybe let me write here. So this one is basically same as 1 equals 2, or 1 equals 3, or 2 equals 2, or 2 equals 3. Because 1 and 2 here are coming from the first set, and 2 and 3 here are coming from the second set. And of course, if you use this way, then why this is bottom is actually obvious. When you make a conjunction over this equality cannot be true all at the same time. Okay? By the way, the homework 2 is okay. So I was thinking maybe giving you separate set of homework problems, but turns out that this lecture note has very good set of problems. So I don't think I have to invent a new problem set for this. The only problem is all the answers are already available in the lecture note. Okay? So homework 2 is study the lecture note, study the problems, all the problems there, and we'll have a quiz. Okay? So next Wednesday, we will have the quiz. You don't have to submit homework. The quiz will replace your homework. Okay? And the problems that I'm going to ask you is almost similar to the problems in the handout. Okay? Yes?
How long do you anticipate the quiz to be? Is it like half the class?
About half the class, yeah. I haven't thought too much about it. Basically, the homework is to encourage you to review the materials, and I think the quiz will do the same here too. Okay, so let's do some exercise. Okay, so what is the propositional image of this? So this is just one line. Okay, so usually the reason that this dot dot notation is used is it actually simplifies the lengthy code. Okay, you don't have to write a very lengthy code. Although if you don't mind writing this, that's also okay. So what is the so let's do the first one. So square 1 dot dot 2 and 1 dot dot 2. Remember this thing, okay? The 1 dot dot is actually in the head, right? So this is actually the whole rule. There is no body, okay? So then what should we do? So it's a conjunction of all possible value substitution. So let me just write square. So this is square 1 comma 1, square 1 comma 2, square 2 comma 1, square 2 comma 2. Okay? So instead of writing this lengthy code, you can just write this. That's it. Good. Okay. Question about the first one? Yes?
When you have the single rule, you don't need to end it in a period?
Very good. Yes, that's my typo.
Okay.
Yes, thank you. Yeah, we need period for every rule. Yes. If you miss the period, Clingo will say the rule is, yeah, somehow it cannot be parsed, and that's actually one of the error that I often find, because period is so small, right? So you don't expect to see, but Clingo always complains about it. All right. What about the next one? So P1 dot dot 3. So this is conjunction, right? So this will be P1, P2, P3. Now let's see. We know that in the second rule, x can be replaced by all possible values from the universe, right? But let's only look at the let's actually do that. So what is the now let's not simplify. Let's just say what will be the instances here. There are two cases. Okay. So one case is when x equals 1, and the other case is when x is not 1. Okay. So when x equals 1, what will happen is true or top. So let's say top if P1, because x equals 1. Okay, so we are talking about propositional image. There should be no variable left over. Now this is the case, but now what about the other case when x is not thing? So let me just write meta variable v. So v is not equal to 1, then this last one is the instances. And how many such instances? There are infinitely many. As long as v is not equal to 1, then this is the case. Okay? Let's think about something. So the last rule is actually infinite, right? So I wrote one line, but actually v ranges over all possible elements in the universe, so it can be many. But are they really that meta? So what are the really necessary rules that we have to consider from the last one? 2 and 3. Why? If it is 4, why? If v equals 4, why don't we need to consider that?
We cannot find it in the database.
V equals 4. P of 4 is never true, right? So then we don't have to worry about it. Remember, we are looking at the minimal models here, right? So when v equals 4, then this is not provable from the program. It's always false. Okay? So then if part is false, then the rule is true. Okay? So yeah, so simplifying this, basically what Clingo will consider inside is not all the set of infinite rules. It will consider, actually let me just go one more step slowly. It will consider these rules. Okay? Now Clingo is actually more intelligent than what I just said. So in fact, one of these 4 rules are actually also redundant. Which one is it?
The first one.
The first one? P1 and P2 and P3?
No.
1, 2, 3, 4. Second rule, right? Yeah. So this is redundant because this rule is also true. When the head is already true, then the rule is also true. Okay? So, yeah. And what does it mean here? So now you understand what is the stable models for this program, right? Stable models here should be the minimal model, right? What is the stable model for this program? So Clingo is a program that computes stable model for you, but you have to understand the concept here, right? So what is a stable model?
There is none, right? Cannot be
There is no stable model. Do you get it? Okay, why? Because the first rule says all of P1, P2, P3 should be true, but the second rule says P2 is false, so this P3 is false. Okay? So that's inconsistent. So there's no model, hence there's no minimal model. Right? Okay. Now let's do the same thing for the next one. So P1, P2, P3. Now this is what? How do you turn into the formula? Is a disjunction, yes. P1 or P2 or P3. Okay. Now, from the second one, we can generate multiple rules. So let's say what can be done. Now, note, one thing that we have to note here is the head is actually empty, right? So empty head is, no, look at this. Head is a conjunction, right? By default, head is about, head is disjunction. Head is disjunction, okay? Empty disjunction is bottom, okay? And if, of course, if you don't remember all these things, it's okay just to remember that empty head means bottom, okay? So this is bottom. Now x, so there are actually 2 cases when the values of x is greater than 2 or less than or equal to 2, right? So let's say if you pick some v from the domain and substitute for x, and let's say this v happen to be greater than 2, then what is the instance here? So bottom if p of v and
True.
top, yes.
Okay.
Okay? So whenever v, the value that you're substituting for, is greater than 2, this is the case. What about the other one? It's actually symmetric, so this will be bottom if v is less than or equal to 2. Good. Now, obviously the last rule is redundant because it's already false here, so the rule is always true. So we can forget about this guy. But now we are left over here, okay? But among these instances also, we can only look at the essential part. What is the essential ones? Only when v equals 3, right? Because v should be greater than 2, right? But if v equals 4, 4 is not even possible. P of 4 is always false, so you don't have to worry about them. Okay? So this one is simply, the essential part is actually only this. So, what are the stable models here? Singleton set P1, singleton set P2. Okay, so there are two stable models, two minimal models. Okay? Question? Okay, so then now we go into the next subject, which I hope I can finish. Okay? And I'm not going to rush if you cannot quickly follow here. Okay? So, yeah, let me know if you have questions. Okay, feel free to interrupt. So far, we didn't have any negation. So positive program, right? So they don't have negation in the program. But now let's apply the negation. The first program is actually still positive. What were the stable models of the first program? Here, the one here. What are the stable models? PQR S, right?
Yeah.
So minimal models should contain at least P and Q should be true because they are fact. Okay, this is actually not the Clingo program notation, so you may see the comma, but just forget about those details. So P, Q must be true because they are the fact that has to be true. And if P is true, then R must be included. If Q is also true, then S must be included. So this is actually the minimal model, which happen to contain all atoms, right? But then the next one is this one, okay? And for the next program, we have this negation here, okay? So the meaning of this is roughly like this. So we are going to add R to our stable model, okay? If P is true, then you cannot derive S, no matter what you do from this program, okay? So remember, when we are doing the positive program, we are doing this iterative procedure, right? We include the minimal things, and if we have to include another one, we increase that set. But what's written here is a bit mysterious. The reason for that is when we are considering whether to include R or not, we have to know whether S could be included or not. But we are still in the process of generating this set of atoms. We don't know whether S will never be derived from the program yet. Still, we have to make the decision to use this rule, whether to include R into the stable model or not. Now note here that this is not a very simple topic. Okay, in 80s, a lot of semantics was proposed to understand this meaning of negation in the logic program. Okay, and there are quite a few definitions about this, and this is termed as negation as failure. This is not the typical negation in classical logic. It works somewhat strange. Okay. For now, I'm going to explain this in terms of intuition. Okay, so let's think without defining the formal semantics. Let's try to assign the meaning, some informal meaning here. So, what could be the stable model? What could be the intended model of this program? for the programs that I wrote here, it's actually a bit easier to think about. So what should be the minimal belief that the agent should have? P must be there. Yeah, no matter what in this case, P must be there. Q must be there. And S must be there. Okay, good. Now S is already derived, which means that not S cannot be true. So this is false. If this is false, then what do you do with R? You don't need, and you close here. So in this case, it's actually fine to say that PQS is the stable model, because we already know from the previous iteration that S was already derived. Now note here that this not S means that S can never be derived from this iteration. But if it happened to be derived before, then this negation of S is false. Okay? So consider negation of S as this way. It was not derived yet, and it will never be derived later. Okay? Then not S is true. Otherwise, not S is false. Do you get it? So informal reading. Okay? You have to include P. You have to include Q. Once you have include Q, you have to include S. But since you already included S, not S can never be true. So the third rule does not matter. Okay, so R has no chance to be included in the stable model. That was the rationale for the second program. Okay? All right, so then let's go to the next one. What will be the stable model? What will be the minimal rational belief that the agent should have? PQ R. How? I simply deleted something and then it changes stable model. Right? PQR is actually the stable model. Why? So P and Q should be there. That's fine. But what about S? From this program, is there any chance that S can be derived? No. S does not even occur in the head of the rule. S will never be proven. No matter how many iterations that you do, S cannot be derived, because S does not even occur in the head. In the case, S is false, so negation of S is true. If negation of S is true, and you already derive P, you must derive R. So the stable model is PQR. Are we together? No? So let me explain again. This one becomes true when S cannot be derived at all. And from this particular program that you see, S cannot be derived because S does not occur in the head of the rule. Remember the iterative algorithm that we did. When you do the minimal model generation, if the body is true, then you have to include head. Right? So those atoms that can be in the stable model are always coming from the head. Okay? But S does not even occur in the head, so there is no chance that S can be proven, or S can be generated. Okay? So remember, this rule is kind of generating the set of atoms from the bottom-up way. Okay? What about the last one? P and R. Any other idea? So why P and R? Obviously P must be there, right? But should Q be there? No, Q is not even in the head anymore, right? So Q cannot be true. If Q is not true, then do you have to derive S? The only way to derive S is when Q is true, but since Q is not derivable, S is also not derivable. If S is never derivable, what about not S? Is it true or false? True. Okay? Then what do you have to do with R? You have to include, because this rule says R must be in the stable model if P is true and S is never derivable. And we just said that S is never derivable. There is no path to make S to be derivable. Okay? Are we together? Okay. Okay, good. So let me just recap this informal reading that I was using. So program pi can be viewed as a specification for generating the stable models, where you can identify stable models of the set of beliefs that the rational agent could have. So stable models here that we see is a collection of atoms. And when you generate this set of atoms, you have to apply this, you're applying this informal principle. First, this rule must be true. Okay, you're using the true rules. Okay, so if the body is true, then head must be true. Okay, another thing is minimality. Okay, so in classical logic, if body is false, the head can be either true or false. But here, if the body is false, then you don't have to include, you shouldn't include head because of that rule. Okay? So it's a rational principle which says believe nothing unless you're forced to do. Okay? If the body is necessarily true, then you have to include the head into your set of belief, which is the stable model. But if the body is false, then don't do that. Don't believe more than necessary. Okay? Okay, that is actually an informal thing. So let's actually do a bit more. Okay, so this is yet another set of examples to illustrate that here. So P if Q, what is the stable model? Empty. This is a positive program. Okay, you don't have to believe anything. Okay, so empty set is the stable model. What about P if not Q? P. Why? Because Q cannot be derived, right? If Q cannot be derived, then not Q is true. Then P must be derived, right? Okay, good. So this is P. Any question here? Do you all follow? Good. What about this? Oh, you guys are good. So why? Because R can never be true. Then not R is true, right? So then Q must be true. When Q is true, then P is true. So PQ, good. What about this guy? Yeah, okay. Q, why? R can never be true. R cannot be derived. So then not R is true, then Q must be true. Q must be derived. If Q is derived, then not Q is false. So you don't derive P. Good. What about this guy? Two stable models, which is P and Q. Now this is a bit tricky. The others are having only one answer set here, or only one stable model. But this one actually has two stable models. Why? Well, assume that P is true and Q is false. Okay, that's what the stable model is saying, right? If you think about this, the P, though not P, is actually false. Okay, so then this rule does not work. But since then not Q is not derived, not Q is true, so then P must be true. And similarly for Q. Now note here that this is a bit challenging. Okay, I don't know. Somebody may have some more idea, but this is the case where the informal understanding does not always work well. Okay. Now what you have to do is you have to guess some possible belief, and from this belief you're generating the minimum belief, and if it happens to be the same as what you believed originally, then this is stable model. Now this idea is called fixed point semantics, and there's actually very brilliant ideas behind these semantics. Okay, Now, this example, you don't have to actually understand the informal reading, informal intuition that I just explained, because that is not to be expected. The others here, though, can be explained through the informal reading. Okay. Now that's where the formal semantics comes in. When you read this as a things, there are sometimes this reading does not always work. Okay, so that's why we are returning to the formal semantics to do, and this is actually one slide to define the formal semantics, which will probably lose half of this class. So my goal is to at least retrieve half of this class to understand this definition. Okay, we are going to do more exercises next class, but it's good to know this now. What we are going to do, you remember the sub-formula finding that we did when we go into propositional logic? Okay, why did we spend some time on doing that? Because of this thing. We have to identify some sub-formulas that we are going to transform into top or bottom. Which part that we are going to do? This is the part of the formula that starts with the negation. Okay? So the formal definition of so-called critical part is a sub-formula that begins with negation, but it's not a part of another sub-formula that begins with negation. In other words, we are looking at the maximal occurrence of negated formula. Okay, it might be confusing, I understand. So let's look at this example. So here not P is negation of Q and not R. Okay, so there are three occurrences of negation. Which part is critical, which part is not? So maybe let's draw the parse tree. Negation, P, okay. Negation, okay. Okay, so you can draw the parse tree, right? So which one is critical part of the formula? Hmm? None of? No. Yeah, so this guy is negation, negated formula, but it's not a part of another negated formula. And same for this guy. So these two are the sub-formulas that are critical. This guy is not. Why? Because it starts with negation, but it is actually inside another negated formula. Okay? So the answer is this guy and this guy. Okay? Are we together? Okay, just look at the maximal occurrences of this negation. Okay? That is not a part of another negated formula. Okay, so the semantics will be in two steps. One is actually, maybe three steps. Okay, the first thing to do is to identify this critical part. The second step is replace this critical part with either top or bottom. Okay. So, which part is going to be replaced with top, which part is going to be replaced bottom, depends on the condition. Okay? Now, I should actually say that we are given this pi as a propositional program, and we have some x, which is an interpretation. Okay? So we are going to transform the program pi into another program, which we call reduct. So here, pi, and then we are given x. Using this, we are going to construct new program called reduct, which is denoted by this pi superscript x. The reduct is obtained from the original program by replacing some critical part, or actually all critical part, with either true or top or bottom. If the critical part is satisfied by x, replace with top. Otherwise, replace with bottom. Okay, so the whole picture is this. You're given the program, and you are given the interpretation. look at some subformulas that start with negation. And that subformula is true under the interpretation, replace with top. Otherwise, replace with bottom. Okay? So perhaps example will help here. Okay? Let's skip that the other definition. Let's actually look at the example. So here we have this gamma, where we can say pi. Let's actually use pi. Okay? So first we consider PQS as our interpretation, which means P and Q and S are true and R is false. We're going to obtain this reduct, and first we have to identify what is the critical part in the original program. What is the critical part? Not S. There's only one negation. Okay, so that's easy. So this part will be replaced by top or bottom, depending on whether the interpretation that you're given here satisfies this not S or not. Okay, so what is the reduct here? So let me just copy all the other part, because they will not be changed. Okay, so not S. Is it top or bottom? Bottom. Because S is true, so not S is false.
It's the visible.
Yeah, okay. Okay, thank you. Okay, so not S is false under this interpretation PQS. So we replace with false. That's it. Okay, the next one. Again, the other part is the same, so I don't have to do anything. But this not S will be replaced by bottom or top.
Top.
Why top?
X is not there.
Because the interpretation says S is false, so not S is actually true. This interpretation saying that S is false, so then not S is true, so this is top. Okay? Easy to do. Good. Now, let me just skip the last one. You can do this by yourself. But now why? So the third step of finding stable model is this. So first step, find the critical part. Second step, replace the critical part with either true or false, depending on whether the interpretation satisfies that part. The third one is, don't look at the original program, but look at the reduct and check whether the interpretation X that you started with is the minimal model of that reduct. If that is the case, then X is called a stable model, otherwise it's not. So this is somewhat too much, right? Okay, so let me just recap the steps, okay? What do you want to do is you want to check whether the X, the interpretation X that you are given, is a stable model of pi. Okay, so remember the input to your decision procedure, okay? Here is the program and the interpretation. The output is saying whether this interpretation is a stable model or not, yes or no, okay? So how do you do? First, given this interpretation, first find the critical part, and then using this interpretation, check whether this critical part is either true or false, and then replace each of the part with bottom or top, okay? Then you get the reduct, and now you go back to the previous definition of stable model. Check whether X that you started with is the minimal model of the reduct. If all these conditions are true, then X is a stable model, otherwise it is not. Okay? All right. So, okay. This is something that I'm going to continue next time, but probably next time we can start with this discussion. So why do we bother with this reduct? What happens if we don't say this is the minimum model of the reduct, but let's say same as what we did with positive program. So if you just consider minimal model of pi rather than minimal model of the reduct, how is it different? So here's a claim that you can try, okay? So X is a stable model of pi if and only if X is a minimal model of pi. Note here that this definition, this claim is actually true if the program is positive. But you'll see that this is no longer true when the program start to contain negation. So I already say this is false, so you can come up with some counterexample. Okay? All right, let's stop here and let's do the exit ticket. So we are going to continue the stable model semantics. More examples will follow. So if you didn't get some idea here, perhaps you can read the lecture note, and next time we'll have more examples to help you understand.